If the Earth is a grape, the Sun is the scale of a massive elephant. It is pretty large, but this is a bit too close. We want to put it 400 meters or 4 football pitches away. Let's upload the other planets of our solar system right here in the Big Apple. There's large Jupiter. It's approximately the size of a beach ball. The remaining major planet is Neptune. It is out past the Statue of Liberty, 11 kilometers away from the Sun. It's about the size of a melon. You can see why it's hard to see Neptune. We're on a grape trying to observe a melon in the dark, almost 11 kilometers away. However, now that we've got our scale sorted out, how large is the smallest naturally occurring black hole compared to the solar system? Well, it would be just this huge, smaller than a fine grain of sand. Black holes are tiny. Obviously, they are much smaller than the Earth. They are about the same size as the asteroid that wiped out the dinosaurs, which is also incredibly small. Black holes can be smaller than asteroids. Isn't that crazy? Now you may think, well, this is a unique tiny black hole that doesn't have much in it, but it's not. That grain of sand started out as an A-type star 10 times wider than the Sun and 35 times the mass. The size of a large hot air balloon on our Earth grape scale. When a massive star like this reaches the end of its life, it explodes in a supernova. I've sped it up here a lot. Most of the star bursts outwards, forming a huge cloud of gas and dust heaps of times bigger than our solar system. But it leaves behind a core of iron and nickel, a bit smaller than our Sun but with more than twice the mass. The iron and nickel atoms just aren't strong enough to withstand the crush of their own gravity. It collapses, and atoms are so empty they almost seem to vanish. When they are crushed, they are crunched down to a clump of neutrons called a neutron star. It is so dense you can see it bend light around it. If it's as heavy as 2.2 suns or more, as it is in this case, even the neutrons aren't strong enough to fight their own gravity. So it collapses one more time to form a black hole. The mass of more than 2 suns is now inside a black sphere just 13 kilometers across. Smaller than a fine grain of sand on this Earth grape scale. But black holes are not quite what they seem. Now, just to get close up with a black hole for a second, a black hole is 2 things. There is something in the center called a singularity and a black sphere around it called the event horizon. Let's chop it in half for a second. Essentially, in the black hole, the singularity is the crushed core of the star. The exact size of the singularity remains a bit of a mystery because it breaks our current theories of the universe. It could have no dimensions, just a dot, or it could just be quite small. We can describe the area outside the event horizon very precisely, but for now at least, the singularity requires improvements to our understanding of physics to fully define. It doesn't help that we can never see it. This is because this crushed star has so much mass that it reaches out with its gravity and pulls everything nearby in, including light, creating this black sphere around it. The event horizon is a cloak of blackness that we think might be just empty. It just marks the point of absolutely no return for anything. But you're not really safe outside it. Gravitational gradient. Small black holes mainly have something called a gravitational gradient. All that means is when you get close, you will inevitably be turned into spaghetti. Seriously, you're pulled much harder on the front of your body than on the back, and it will just stretch you out more and more the closer you get to it. It's called spaghettification. With truly massive black holes, that doesn't happen until you're in the event horizon. But whether it's inside or outside, you can't avoid gravity. When you get near the singularity, you will inevitably be ripped to shreds right away. I often hear people say they'd like to fall into a black hole just to see what's inside. But I wouldn't advise it. If you're lucky and it's a huge black hole, and you can avoid all the other matter falling in with you at tremendous speeds, you'd pass the event horizon, and you'd probably momentarily see only darkness in the direction of the singularity, not be able to tell anyone about it, and a fraction of a second later you'd be instantly turned into spaghetti. Black hole size. So this is the theoretically smallest black hole we can have, but the smallest we found is a little larger and probably around 6.3 solar masses in weight. It's the size of a fine grain of sand. If you thought it was hard to find a melon-sized Neptune, imagine trying to see an absolutely black grain of sand in the blackness of space way outside the solar system. We have to look for either its big gravitational impact on things, its ability to bend light around it, or the extremely high light given off when things fall inside them. Black holes and galaxies. So why have I made this massive scale model of the solar system? If black holes are the size of grains of sand, well, it's because black holes don't just like eating spaghetti. They like eating stars too. So to understand the next bit, we need to talk about galaxies briefly. We live in a galaxy, the Milky Way, about right here. We're still learning a lot about how galaxies form, but in the early stages, there's a lot of matter and young stars in the center of this mass. And that means massive stars absorbing each other and becoming black holes. In reality, there are likely to be black holes absorbing other black holes, making these massive black holes grow larger and larger, eating more stars, matter, and black holes. Eventually, only one wins, and that winner is a supermassive black hole. They're obviously right in the center of the galaxy. We now believe there is one at the center of almost every galaxy. We have one at the center of ours. We've even taken an image of it. It's called Sagittarius A star, and it's massive. The smallest black hole has a mass of a little over 2 suns, while Sagittarius A asterisk has a mass of 4.3 million suns, which is ridiculous. Now, the reason it has this bright ring around it is that it's currently eating a star. That's the gas of that star being ripped away and accelerated to great speeds and temperature before being pulled into the event horizon. It's a flat ring of material, but it looks like it's above and below it too because the black hole bends the light around it. It's an optical illusion. How large is it? So how big is this thing on my solar system scale? If it's got 4.3 million suns in it? Well, black holes are a bit underwhelming in terms of scale because they crush massive things into tiny things. What's impressive, really, is their crushing ability and how much they can fit inside them. So if I just showed you its size, I don't think I'd be doing it justice. So I thought the most interesting way to visualize a 4.3 million solar mass black hole might be to watch one grow by feeding it 4.3 million suns. So here they are. The amphitheater of light. This ridiculous amphitheater of light is what 4.3 million suns look like on this scale. I've had to make this canopy of stars 50 kilometers in diameter so that we can see the individual stars. I've placed that grain of sand-sized black hole where my hand is right here, near our own sundae. So that will be the first one to be eaten. This is generally how stars are absorbed. They are stripped of their matter, forming this accretion disk. We're going to have to speed this up in this crude simulation. In reality, the process to gain so much mass probably takes hundreds of millions of years. But by actually seeing the equivalent mass that this black hole has eaten, it should hopefully give us a better sense of scale of just how massive Sagittarius A asterisk really is. When I first started this video, I knew the numbers, but I couldn't wait to see this. To actually see what 4.3 million really means. You can fit more than 1 million Earths within the sun, and each of these dots is a sun in this almost infinite sea of light. It should also be noted that the sun is actually an unusually heavy star. It's heavier than 95% of the stars in the universe. So 4.3 million suns of mass is even more impressive. As Sagittarius A asterisk continues absorbing stars, it will eventually reach 70 meters in diameter on this scale, about 20 times wider than one sun, but containing the mass of all of these. It's actually not very large at all. It's just the size of a large star. It wouldn't reach the planet Mercury. And for instance, it's much smaller than the star Betelgeuse in the constellation of Orion. So if you already knew there was a supermassive black hole at the center of our galaxy, you might have envisaged this terrifying, massive object slowly sucking up the galaxy. But it's not. It's this incredible black star-sized object of immense power. Just don't get too close to it and you'll be fine. Ton 618. There are even larger supermassive black holes, too. The biggest we've found so far is inside a quasar called Ton 618. A quasar is an extremely bright center of a galaxy. It's like a lighthouse. And quasars are the brightest things in the whole universe. They're powered by an ultramassive black hole, accelerating matter to incredible speeds and temperature, blasting out energy from the black hole's accretion disk, forming jets of plasma bursting out to the poles of the black hole. The TON 618 black hole is even larger than 70 meters because it has more solar masses in it. So let's feed it those extra suns and let's have it grow from the Sagittarius A asterisk-sized black hole to the size of TON 618. So on a scale where the Earth is the size of a grape, the sun is the size of an elephant, and the smallest black hole is the size of a fine grain of sand. The black hole TON 618 is about 650 kilometers or 400 miles in diameter. It's 27 times the diameter of the solar system out to Neptune. It has the mass of 41 billion suns. This single black hole has more mass than our entire galaxy, the Milky Way. We think of black holes as star eaters, but really they're galaxy eaters. Outro. Thank you for watching my video on the scale of black holes. I hope you enjoyed it and perhaps learned a bit about these crazy little star crushers. I'll be doing more on them in another video as there are some things I didn't touch on. If you haven't seen my other videos, there's a short playlist here. If you're enjoying them, please feel free to like and subscribe, ring the bell, etc. It's just me making these videos, and I hope to make them full-time at some point. So any support is greatly appreciated. And on that note, if you'd like to support me further, I've got a Patreon link in the description where you can join my little group of astronauts here. They're amazing. T-shirts are also available now, too. Shameless self-promotion time. Otherwise, thank you again, everyone, for all the incredibly kind comments on my videos. I love making them, and I love to hear your feedback and suggestions. If you've got any questions about space and science and the universe, do please feel free to ask me in the comments, too. I always love to talk about that stuff whenever I have the time. Cheers.